Hello dear students, welcome you all. So in this lecture I am going to discuss about the QPSK modulation technique, right? QPSK stands for quadrature phase shift keying, right? So it is basically a type of M-array modulation technique. Uh, In the earlier lecture, I have explained all M-array modulation techniques that contains M-array ASK, M-array FSK, M-array PSK, right? So in this lecture, now I'm going to discuss exclusively about the M-array PSK modulation technique. And quadrature phase shift keying is basically a type of M-array PSK modulation technique, right? We know very well what is M-array modulation technique. We know that in case of M-array modulation, we are using M levels of either amplitude, frequency or phase of the resultant modulated signal, right? And M is equal to 2 raised to power n. Here n is the number of bits. All these things has been explained in the previous lecture. So I'm recalling equation that I have written there. That equation was B of M array PSK, M PSK, that was written as A cos of into 2 pi vega C, not vega C, 2 pi FC T, 2 pi FC T plus phi I, right? It is taken for a time is taken for interval greater than 0, less than equal to T, S and I goes from 1 to so on M, right? And the expression for phi I was 2 pi upon M into I minus 1 plus constant, right? So I have told you that two situations arise. The one situation is when we are taking constant is equal to 0, that will give me the value of q I and for different values of I, and they were as if I put the values there, I will get 0, pi by 2, comma pi and 3 pi by 2, right? So this type of M-array PSK was known as a conventional PSK, right? But if we take C is equal to pi by 4, then I got the value of phi I. I have explained it in the early lecture also. It was pi by 4, 3 pi by 4, 5 pi by 4 and 7 pi by 4. So this was known as pi by 4 QPSK. Although both these modulation techniques are called as a QPSK, quadrature phase shift keying, right? Both these techniques are called quadrature phase shift keying techniques, but this is called pi by 4 QPSK because we are using the value of constant equal to pi by 4. So this is about the quadrature phase shift keying modulation technique. So as I explained here that we can have two different QPSK, conventional QPSK, that is when C is equal to 0, right, and pi by 4 QPSK, right, that is when C is equal to pi by 4, and in that case the phase angles that we are going to use, they are pi by 4, 3 pi by 4, 5 by pi by 4 and 7 pi by 4. So now I'm focusing on this one, right? So Now the next thing is how we can create a QPSK signal, right? That is pi by 4 QPSK, right? Because it is the commonly used M-array modulation technique. So I am discussing it now in details, right? So for that, let's consider a bit stream. We are given a bit stream. Let that bit stream is 1 1 0 1 1 0 1 0 1. Let this is the given bit stream, right? Input bit stream. First of all, we will identify the odd bit and even bits. So this is odd 1 3 5, right, 7 and 9, right? These are odd bits. These odd bits are also known as in phase bits. In phase bits. Whereas this is 2, 4, 6 and 8. These are even bits, right? And they are also known as quadrature, or we can say they are pi by 4, or simply we can say quadrature phase bits. In phase and quadrature phase bits, or in phase bits and out of phase bits, we can also say that. So even bits are taken as pi by 4 phase bits, and the odd bits are taken as in phase bits. So the first thing in this QPSK modulation is to separate even bits and odd bits, and the odd bits will be taken as in phase bits, whereas the even bits will be taken as pi by 4 or quadrature phase bits, right? Then when we will take two bits, if I am taking we know m is equal to 2 raised to power n. Now if I take n is equal to 2, means we are taking the combination of two bits, so m will become 4, right? I mean, I will have 4 different levels, right? They are called symbols. 4 symbols are used for representing the information, or 4 different levels are used, and 4 different angles will be used, right? You can see here, this is also the case when m is equal to 4, right? Now n is equal to 2 means we are considering the combination of two bits, this, this. So you can see from here, we are taking the combination of one in phase bit and one quadrature phase bit, right, in all these cases. So this is the way of doing the QPSK. I'm showing you how it is achieved in actual practice. So to understand it, let's take this table. So in this table, I have taken a bit stream as 1, 0, 0, 0, 0, 1, 1, 1. So you can see here 1, 0, 0, 0, 0, 1 and 1, 1. You can see here in this table how the corresponding symbols, that is levels of the phase and phase shift are created. So you can see here when I is equal to 1 for these two input bits, symbol is S1, and the phase difference will be obviously it is a cos of vega ct plus pi by 4, and the phase shift is pi by 4. Similarly, when I is equal to 2, the next bit labels are 0, 0, right? It is called S2 symbol, and again this thing will remain as it is, and we will get 3 pi by 4, phase shift is 3 pi by 4. Similarly for other bits, right? Combination of two bits. So you can see here that the phase difference between the adjacent symbols or adjacent levels is pi by 4, right? So now I'm going to show you the actual diagram, that is explaining the working of pi by 4 QPSK modulator. one thing that I tell you, that how I can generate this Q pi by 4 QPSK. It is by simply taking two carrier waves which are 90 degree out of phase, and then mixing yeah, modulating, we can say, the odd bit stream with one a carrier, and even bit stream with other carrier. So these two carrier waves are 90 degree out of phase, and then after these bit streams are added together, right? And the result will be in such a way that we will get different levels or different symbols in the modulated QPSK, which are having phase separation of 90 degree from each other. It was not pi by 4, but it was a 90 degree. Earlier, I think I told you wrong, that the phase difference between in them is a pi by 4, because you can see here it is pi by 4 plus pi by 2. That's why you are getting 3 pi by 4, right? So when you will see this diagram, you can see here, you can understand it now. So this input bit stream, what is coming from here, that in this case it was 1 0 0 0, then 0 1, and then 1 1. So first of all, this bit stream, input bit stream, is sent to a bipolar NRZ encoder. You know very well that what is the meaning of bipolar NRZ encoder, right? It will change the input bit stream from the levels that were earlier 0 and 1. I can draw here a diagram, you can understand it in a better way, right? Let this is the input bit stream, that is 1, and then it is 1 0, then 0, then again 0, so on, 0 0, then again 1, right? So this is the format of returning 0, RZ format. But when I convert it into NRZ, right, it is 1, then 0 0 0 0 1. When it is converted into non-returning to 0 format, this will become this bit stream will become kind of in this way, right? 0 0 0, then again 1, right? In this way, 1 0 0 0 0 and 1. So this is the output of this bipolar NRZ encoder, and then it is represented as VT. Now then it is sent to a series to parallel. S to P means series to parallel converter, means its task is to separate the even bit stream and odd bit stream, right? So this is odd BOT and this is even bit stream, right? Then these two signals are separated, and then they are sent to a product modulator. This is what? Product modulator. And what is the task of product modulator? The task of the product modulator is to modulate, right, this carrier wave. Now it is very important, you can see here, this carrier wave is A cos of vega ct, and this carrier wave is A sine of vega ct. Both of them are 90 degree out of phase, right? Now here this odd bit stream or odd bit NRZ data is sent to this product modulator, so it will change this carrier wave according to it. Similarly, the input bit signal is sent to this product modulator, and it will change the this carrier wave according to it. And then after I will get this one, right, multiplication of these two, and this one multiplication of these two, and then after these two signals are added together by using a adder, right? You can see here I am using a adder. The resultant signal is a B QPSK, that is S odd T, as even t. They are represented here. So this is the way of working of this pi by 4 QPSK modulator. What we did, we simply took the input bit stream, then converted it into a bipolar NRZ format, then after separated the even bit stream signal and odd bit stream signal from that, right? I mean, you can see here, this is, if this is even bit stream signal and this is a odd bit stream signal, this one is odd, so odd bit stream signal is separated and even bit stream signal is separated by this series to parallel converter. Then after, these two signals are used for modulating these two different carrier waves which are 90-degree out of phase, and then these are added together resulting in a QPSK modulator wave, that is pi by 4 QPSK modulator. So this is the way of working of this QPSK modulator, right? Now you can see here one more example there in this diagram, that is in this case I have taken the input bit stream as 1 0 1 1 0 0 0 1 and 1 1, right? It is represented as here, this is odd bits, odd bits, odd bits, odd bits, odd bits, and these are even bits. In blue they are even bits, this one, right? So first of all, this is odd bit stream, you can see here, right? Odd bit stream was 1 1, then 0 0, you can see here, and then 1, right? So this is the NRZ format of this odd bit stream. Here the bit stream is different from the earlier, but it is quite easy to understand how the bit stream is converted into NRZ format, and then after the even bit stream and odd bit stream format are separated. So this is B odd bit stream NRZ format, and this is the corresponding the modulated wave, for which we have used what, cos of vega c t. Here A is taken as under root PS, so forget about it. So I am taking it A cos of vega c t multiplied by B out. So then after, what will happen? You will have a change of phase. You can see here 0 1 0 1 1, right? Corresponding to these bits. Similarly, this is the even bit stream. This is 0 1. You can see here 0 1 0 1 and this one. So this is now the second case. Here it is A sine of vega c t multiplied by V even bit stream into t, and then after these two are added together, right? So you can see these signals, this one and this one, right? Both these signals, you can say, they are simply binary phase shift keying signals. This one and this one. This is also BPSK signal. How this way we have taken this way when 1 and this is 1 1. You can see here we have one wave, right? Here when it is 0, 180-degree phase difference induced, then 0 0, then again when we are going from 0 to 1, 180-degree phase difference, right? Similarly, in this case, you can see here 0 and then it is 0 1, 0 means this, right? 1 means 180-degree phase difference. So 0, right, and then 1, you can again see the difference. So this is the way there's these two different carrier waves are modulated by BPSK, right, technique, and then after these two signals, this one and this one, they are added together to generate the resultant B QPSK wave. You can see here. Now in this B QPSK wave, the phase difference between the this resultant wave and the carrier wave, original carrier wave, that is pi by 4, right? And here the phase difference is 7 pi by 4, right? Here the phase difference is 3 pi by 4, here it is 5 pi by 4, it is again 7 pi by 4. So this is the difference between different symbols or different levels. The first level is 1 0, then we have a 1 1, right? 1 0, the phase difference is pi by 4. 1 1, the phase difference is 7 pi by 4. 0 0, it is 3 pi by 4, and then 0 1, it is 5 pi by 4. It is again 1 1, 7 pi by 4. So I can tabulate it here: 1 0 1 1 0 0 and then 0 1. So corresponding to it pi by 4, corresponding to it 7 pi by 4, corresponding to it 3 pi by 4, and corresponding to it 5 pi by 4. So this is what we got here in this diagram, right? How we achieved it? We consider a bit stream, right? Whatever choice we have, but at the end of this discussion, we arrived at a conclusion that the phase difference between the adjacent symbols will be according to this pattern, right? The phase difference is of 90 degree, pi by 2, but it is in this pattern. From 1 0 to 1 1, it is 7 pi by pi by 4 to 7 pi by 4, right? And from you can calculate the phase difference, right? But the adjacent are 1 0 0 0 and then 0 1 and then 1 1, right? So this is the way, right? Now here I am drawing the phase diagram of this pi by 4 QPSK signal. So you can see here the phase diagram. Here I am representing A cos of vega ct, it is minus A cos of vega ct. It is A sine of vega ct, it is minus A sine of vega ct, right? This is first quadrant, it is written here. Second quadrant, this is third quadrant, and this is a fourth quadrant, right? Now in the first quadrant, as you can see from here, as I go from here to here, I can write this vector as a sum of A cos of vega ct minus A sine of vega ct. You can see here, right? So what is this? This is when B odd bit is 1 and when even bit is minus 1, means it is 0 1 0, because when we have taken the NRZ format, then 1 is represented as 1 and 0 is represented as minus 1, right? In NRZ format, right? In NRZ format. So you can see here in this case, B odd bit is 1 and even bit is minus 1. So that's why we got S1T. S1T means combination of these two bits as A cos of vega ct minus A addition of these two vectors, this one and this one. You can see here, right? Similarly, when you reach here, this vector will be represented as S2T is equal to minus A cos of vega ct minus A sine vega ct, and it is possible when both the bits are 0 0, because only then they are minus 1 in the NRZ format, right? So this is represented here. Odd bit is minus 1, even bit is also minus 1. Similarly, the next situation is, right, odd bit is minus 1 and even bit is 1. It means 0 and it is 1, right? So that's why in NRZ format it is minus 1 and 1. So this is represented here as 3 is minus A cos of vega ct plus A sine of vega ct. This is the resultant signal. Similarly, in the fourth quadrant 1 1. So now you can recall this table, right? This discussion, that what is the phase difference between phase angle difference between the adjacent symbols. Now from as we go from here to here, right? From where? From 1 0 to what is the next one? It is 0 0. It is 1 0 and it is 0 0, right? So the difference is, it is pi by 4, right? So as we go in this you can see here, for 1 0 it is pi by 4. So the phase angle is pi by 4. So as we go from here to here, right, the phase angle is here, it is 3 pi by 4. It is basically 0 0. So you can say 3 pi by 4. 0 1 5 pi by 4. So you can see here it is 5 pi by 4. Similarly, it is 7 pi by 4. So these are the different phase angles, right, that are induced in the resultant symbols in the resultant modulated QPSK wave, right. So this is the phase diagram and understanding of this phase diagram of this QPSK pi by 4 QPSK signal. So this is about the working of pi by 4 QPSK M-array modulation technique, right? We have seen here that how this pi by 4 QPSK works and how a phase difference of 90 degrees induced between the different symbols, right? As far as advantages of M-array modulation technique is concerned, we have seen that the main task of and main advantage of this M-array modulation technique is to reduce the requirement of bandwidth. So it has been proved that in the pi by 4 QPSK, the required bandwidth is half to the BPSK, right? So it makes the bandwidth requirement half as compared to the BPSK, that is binary phase shift keying modulation technique. It also increase the data rate or bit rate, we can say in that way also. But it is very difficult to handle, or this signal are difficult to decode and encode. The chances of introduction of error and noise are high. So it is actually a very complex system, complex kind of modulation. But the advantage, that is the requirement of less bandwidth, it is more important than other factors. So this pi by 4 QPSK is commonly used in all communication devices, right? So thank you very much.